Alright, so good morning, student. What we will do today is have a quick revision of the concept of different types of modulus. Okay, so let's start the lecture. Before I start this, please don't forget to subscribe to this channel because you will see fantastic physics explanation, lot of concept builders, and practice questions on this channel. All right. So this video lecture has certain qualities to it. I am going to discuss two very important concepts in this particular video. In the end, they're highly conceptual ideas. They're very useful for your competitive examination. They may help you score more marks than others. So don't forget to watch the two concepts, unique concepts of this chapter right at the end of this video. To understand these concepts, you must go through the whole video and then you will be able to appreciate the last two concepts, which are the very important concepts pertaining to the elastic constants, namely B, G, Y. So let's start. The goal today is study the moduli of elasticity, the relationships, and some important concepts of moduli of elasticity. So the three moduli of elasticity we will study are as follows: bulk modulus, rigidity modulus, and Young's modulus. These are the three moduli of elasticity we will study, and then we will study the relationship, the definition of these. Let's start it. Okay, so first of all, the concept of modulus of elasticity is all about resistance to something, right? For example, the bulk modulus is resistance to compression, right? The is basically a measure of how resistant is the material to change in volume. If a material is offers a lot of resistance to change in volume, its bulk modulus is going to be very low. You're not able to change its volume to a large extent by an application of pressure. So what you do is you apply a pressure, right? And what you're able to get is a very small value of volume change. That means the material is offering a lot of resistance to the change in the volume, right? You can't change its volume by application of pressure. So the bulk modulus is high, right? And later on we will study an example of this. However, if the small application of pressure results in very large change in volume, then the bulk modulus is very, very low. Thank you. Modulus is going to be very low. You're not able to change its volume to a large extent by an application of pressure. So what you do is you apply a pressure, right? And what you're able to get is a very small value of volume change. That means the material is offering a lot of resistance to the change in the volume, right? You can't change its volume by application of pressure. So the bulk modulus is high, right? And later on we will study an example of this. However, if the small application of pressure results in very large change in volume, then the bulk modulus is very, very low. Thank you. Studying the value of what is the G, right? So G is the resistance to change in the shape of the body. How do you measure it? Using rigidity modulus. So if the value of the rigidity modulus of a substance is high, then what we are saying is this material is very difficult to change when it comes to shape. You cannot change its shape very simple. If the material has very low value of G, then you can easily change its shape. This is what you mean by the, so for example, I've given the G, the steel is very high. Deformation of steel is very difficult. The deformation of rubber is very easy, right? You can change its shape easily. So the G value is very, very small. This is the significance of the G, which is very important. In the case of G, the way you apply force is parallel to the surface, right? Now what happens is there is relative motion between the layers of the substance. So if this is a material with this much thickness and I apply a force, then the relative motion between the layers result in the deformation of the substance, right, which is a change in shape. So in the case of the rigidity modulus, what we're dealing with is the tangential stress, which results in relative motion between various layers. Very important definition of what's happening inside when we're studying the mechanical properties of a material. Don't also forget to join the community. All right, so let's start the first modulus. Okay, the first modulus is the bulk modulus. Okay, it's a quick revision, so I'm not going into detail of it, but we will just study the formula and the meaning of it, and we will proceed like that. Okay, so bulk modulus B is minus delta P, the change in pressure, divided by the change in volume per unit volume. Okay, so delta V by V. What exactly is delta P? So delta P corresponds to a compressing pressure. For example, you compress something and the volume changes, right? You compress something and the volume changes. That is what we are referring to. Now, what is a way to look at compression, right? If a body is highly compressible gas, for example, okay? If you have a gas and the gas is highly compressible, which means by applying a very small pressure, right, you're able to get the change in volume. Then we say it's a very highly compressible gas, and the bulk modulus for the highly compressible gas is very low. The bulk modulus of a highly compressible gas is very low because you're able to get a very large amount of change in volume when you apply a small change in the pressure. So generally in the compression situations, you will see the concept of bulk modulus. That's number one. Okay, a very important thing to note in the formula of bulk modulus is the negative sign. What negative sign tells you is if you apply a pressure, which is increase in pressure, the volume decreases. So when you're doing the numericals of bulk modulus, put delta V as negative. If the pressure, because the pressure is compressive, the volume is likely to change, and therefore the negative sign of the volume change will get cancelled with this negative sign. So value of bulk modulus, which is an elastic constant, is never negative because the delta V is negative. That negative cancels with this negative. This negative only tells you the relationship between the pressure change and the volume change. A positive pressure change results in decrease in the volume, which is a negative thing, right? This is the only significance. The value of B, however, always remains positive. We already studied the definition in the introductory part of the video, so I have not repeated. I have only focused on the formula aspects. I hope this helps. Bulk modulus of a quantity is very large. The bulk modulus comes out to be a larger value. What it indicates is you cannot compress it easily. So the change in volume you will get is very low for the amount of pressure you have applied. So delta V becomes very small and delta P is very high. Therefore, B comes out to be a very large value. Very important concept. Second bulk modulus which we study in this chapter is the concept of shear modulus. Right? The shear modulus is expressed as a G, and it is written as shear stress upon shear strain. Shear stress upon shear strain, or F tangential, which means the stress you're applying is tangential to the surface, something like this, right? And the lower surface is fixed, so the upper surface goes a bit. You can see the details later on, but it's a quick revision for your JEE mains examination and school examination so that you can do the numericals very quickly and recall the concepts you have already studied. So this, I put the whole chapter in one place. All right, so tangential stress is shear stress divided by shear strain. What is the shear strain? It is delta x by L. What is delta x? Delta x is the lateral displacement, okay, which is this displacement, right? The extra displacement the other surface has undergone. So this is F tangential upon A, the shear stress. The shear strain is delta x upon L, okay? where L obviously is its original length, right? And it moves by an amount delta x. That's a strain. Delta x by L dimensionless. Let's go to the third modulus, which everybody knows is the Young's modulus. Young's modulus is stress upon strain. It is not shear stress upon strain. It is stress upon strain. And you can see F by A divided by delta L by L. This is what is the Young's modulus. A very important concept in the case of, for example, the rigidity modulus, which is your G, is the steel, right? Steel exhibits very high rigidity modulus. Okay, this is an example of a body exhibiting very high levels of rigidity modulus. Its an example is steel. Now, another very so we have done the definition and the formula of each of the concept: bulk modulus, rigidity modulus, and the Young's modulus. Quickly, right? We have not tried to expand on this. If you want to see what they mean, go to my playlist, which I will share the link below. Go and watch it. Now, let's see this. The a very important concept which is there is when the Young modulus is involved, and there is a strain which is in line with the length of the wire, is the concept of work done against restoring force. When you pull a wire, the stress is produced and a strain, the length is changed a bit. Then whatever work you do to pull it down, right, is stored in the body in the form of potential energy. But remember, this formula can be used only when you have the elastic limit. Okay? Within the elastic limit, everything you will do is within the elastic limit. Now, what is the work done? Work done is half stress into strain into volume. Memorize this formula. You might know it, so quick revision. Half stress strain into volume. Work done is equal to half F by A delta L by L. Volume of the wire is area of the wire multiplied by the length of the wire. So substitute the values of delta L by L. Finally, what you get is this is a small step you do to get rid of delta L by L. This is your net answer, right? Half F square L divided by AY. Y is fixed for a material. It doesn't change during the experiment. Remember, this is to be used within the elastic limits of the material. Okay, so work done is an important concept again. These were definitions, work done. Let's move into the Poisson ratio. This is a very important ratio. A lot of students ignore this and don't study it for the exam. But let's do it. So it is again a negative, right? So you can see the negative mark here. What does it mean? Okay, let's study first. Lateral strain divided by longitudinal strain. Where did you study lateral strain, right? You studied lateral strain in rigidity modulus. And where did you study longitudinal strain? You studied longitudinal strain in Young's modulus. So somewhere there, right? So the Poisson ratio is ratio of two strains. The lateral strain divided by the longitudinal strain with a negative sign. So this is the way you write it. Delta D by D, delta L by L. Obviously, if you, for example, pull a wire, right, the width of the wire or the diameter of the wire will reduce and the length will go up, right? So this particular strain, which is the length changing, is basically in the denominator. Delta L divided by the original length of the wire. And in the perpendicular direction, which is the lateral strain, the diameter, if you pull the wire, the length increases, but the diameter goes down. So this is the longitudinal strain, which is perpendicular to the lateral strain. Okay, so it is mentioned as delta D by D divided by delta L by L. Put a negative sign. Now let's take an example of the significance. Take a cork, a bottle cork. Try to pull it up. Nothing will happen, right? And the longitude, so you may be able to see something in terms of the lateral strain, but the longitudinal strain, that means you won't be able to change the diameter of a cork. For example, this is my pen, right? I can pull it, hardly notice any change in its width, right? No width. Even if I pull it like this, hold it like this and apply force, I'm applying force, doesn't happen. So we say that the Poisson ratio, which is the ratio of two strains, is 0 for cork. Cork is an example of Poisson ratio being 0. Second example, rubber. If you pull rubber like this, right, you are able to see some change in its length and the diameter. It becomes narrow, right? Pick a rubber band in your house and pull it like this. So you will see 0.5. Now let's talk about the negative values of Poisson ratio. If you see foam, right, right, it exhibits negative value, right? It doesn't show you the behavior you expected actually, which is if you increase the length of the foam, the diameter will go down. So if you see negative values, of Poisson ratio, right, you're probably referring to a quantity like foam. Okay, I am not getting into detail of this. So just for your knowledge, these values help you analyze the situation, what type of material it could be, right? So Poisson ratio. So we have studied four, right? One is bulk modulus, rigidity modulus, Young's modulus, and one more, which is a Poisson ratio, which is to do with the ratio of the two strains. Important. Now, a lot of questions in the examination are directed to linking all these, right? So you have to link all the ratios and memorize all the formulas because it helps you solve certain problems in JEE mains, NEET examination, AP physics, or whatever board you study in the class also. Now, this is one formula that you need to remember. Okay, this is the linkage between the Young modulus and bulk modulus of a material. Same material, the bulk modulus is B, the Young modulus is Y. How do you link them? So this is the formula, right? It is 9 by Y is equal to 3 by Poisson ratio plus 1 by B. What you will find when you try to link the different modulus of the same material, a Poisson ratio makes an appearance. Most of the time you will see that, right? If you see, I'm trying to link Y and B, but a Poisson ratio has come in. So memorize this formula also. You can get a question, Young modulus is given, find the bulk modulus. Indirectly, the question may be on bulk modulus, but Young modulus is given. So first convert the whole thing into bulk modulus and then start doing the numerical. First two formulas are the same, right? The second formula you have to know is how do you link the rigidity modulus with Young modulus. This is another expression. Again, you can see the Poisson ratio is what is going to make it very, very important. Linkage between two modulus. In this, we linked the bulk modulus and the Young modulus. In this, we have linked the rigidity modulus and the Young modulus. Okay. Now, if you have to combine these two and eliminate the value of the Poisson ratio, right, which is making appearance in both the formulas here and here, you will get this expression, which is Y is equal to 9BG, B plus G, 3BG. Memorize this expression also, very, very important. Okay, so memorize this expression. This links all the elastic constants in one place. Okay, I hope this helps you understand what are the formulas available to you to link each other. So you may get a question where you have to calculate one elastic constant, and you may have to do two steps using these, right? So one and second. So equation number one, equation number two, and equation number three. And of course, the bulk modulus, the three elastic constants. How do you calculate them? Those expressions are also known to you. So you may find them from here and use them here. Sometimes they do ask you about it, right? So I hope this makes sense. And you can also see the formula Poisson ratio. So, all right, so let's link the bulk modulus with the Young modulus. So the first two formulas are the same, right? The second formula you have to know is how do you link the rigidity modulus with Young modulus. This is another expression. Again, you can see the Poisson ratio is what is going to make it very, very important. Linkage between two modulus. In this, we linked the bulk modulus and the Young modulus. In this, we have linked the rigidity modulus and the Young modulus. Okay. Now, if you have to combine these two and eliminate the value of the Poisson ratio, right, which is making appearance in both the formulas here and here, you will get this expression, which is y is equal to 9bg plus g 3bg. Memorize this expression also, very, very important. Okay, so memorize this expression. This links all the elastic constants in one place. Okay, I hope this helps you understand what are the formulas available to you to link each other. So you may get a question where you have to calculate one elastic constant, and you may have to do two steps using these, right? So one and second. So equation number one, equation number two, and equation number three. And of course, the bulk modulus, the three elastic constants. How do you calculate them? Those expressions are also known to you. So you may find them from here and use them here. Sometimes they do ask you about it, right? So I hope this makes sense. And you can also see the formula Poisson ratio. So here comes the very important part of this video in the end of it, right? Most important topics which you would not see mentioned anywhere. Now, the of the three modulus of elasticity or the elastic constant you studied, which one is the largest one, right? And which one is the smallest, and why? That's a fundamental question, right? Now, if you consider the bulk modulus is the largest. Why is the bulk modulus the largest for a material? The reason is you're dealing with interatomic distance change. You are compressing the material to change its volume. How does a volume change? The volume change because of change in interatomic distance. Changing interatomic distance is tough. Even you apply very high value of pressures, the compressive pressure, the uniform compressive pressure, the change in volume, which is brought by the change in interatomic distance, is very low. And therefore, if you see the B as a ratio of delta P upon delta V by V, the value of B is very high because it deals with change in interatomic distance. Changing interatomic distance is very tough, right? Now, why is G the smallest? Why the resistance to deformation is the smallest? Again, at interatomic level, what it involves is this: the relative orientation of the atomic planes. Here you're not dealing with interatomic distance. You're dealing with deformation of one layer, which is the atomic layer, and its relative motion with respect to the lower layer, which is easy to achieve, right? As compared to changing the whole distance between the interatomic distance, right? Changing interatomic distance is very, very tough, but changing the relative orientation of atomic planes is easy. And therefore, G is very small because it involves change in shape or the change in relative orientation of atomic planes. Second, and a very important concept, which I told you I will do right at the beginning of this video. Remember that the velocity of sound, right, is completely dependent on bulk modulus and is given by square root of B divided by rho. This concept will help you solve many, many numericals. And therefore, the point is that the bulk modulus also finds application in finding the velocity of sound. A lot of material which you study is for engineering purpose. So you also want to know how does the material behave when the sound waves pass through it, right? So materials are subjected to oscillations, materials are subjected to stress, torsion. You don't need to know torsion, but many other things like what is the velocity of sound and stuff like that. And therefore, when you study the material property, the speed of sound is also very important to find out. So it is completely dependent on the mechanical property of the material, okay, which is in terms of an elastic constant, which you have already studied, called the bulk modulus. Two important, very conceptual questions for you to know and help you solve many, many conceptual problems, reasoning assertion, and one markers. Thank you very much, and I hope you like this video. Please don't forget to subscribe to this channel because this is the only channel which is giving you detailed explanations. Thank you very much.